Previously, we saw that the understanding of wireless channel is very important in designing of the transmitter and the receiver. And in the previous video, we also briefly discussed about the large-scale propagation model. So currently, we are looking at the small-scale propagation models. In particular, we will see what happens to the received signal at the receiver when it passes through multiple paths. And this understanding of the channel is very important. And as you know, this MIMO communications, they have evolved so much because the channel has been well understood. So now to begin our discussion with the small scale propagation model, we will make some assumptions. So the first assumption is we assume that the mobile or receiver is moving with some velocity v in the x direction, and there is an angle of incidence theta n of the plane wave that is arriving at the receiver from the nth path. And also we assume that there is a large separation distance between the transmitter and the receiver. And why we are assuming this? Because when an EM wave is propagated from the transmitter due to the large separation distance, what arrives at the receiver is a plane wave. And because of this, it helps us to understand the 2D propagation model. So now when the mobile is moving with some velocity, we know that it will encounter Doppler. So we will have Doppler shift. And this is represented by Fd, n, because in every path will experience the Doppler shift. And this is equal to Fm cos of theta n, where Fm is the maximum Doppler frequency, theta n is the angle of incidence of the nth wave at the receiver, and cos theta n is the component of that frequency in a particular direction. And from the physics, we know that Fm is equal to v by c into Fc, where v is the velocity of the receiver, c is the speed of the light, and Fc is the carrier frequency. Now, as we increase the velocity of the mobile, the maximum Doppler frequency will increase. As a result, the Doppler shift across the nth path, Doppler frequency across the nth path will increase. So typically in communication system, what we have is ideally there is nothing happening between the transmitter and the receiver. When the transmitter sends a signal at the receiver, there is an addition of AWGN noise, which is due to the analog component in front of the receiver, or mainly due to the analog to digital conversion. So we just have an addition of AWGN noise in the transmitted signal. But now we are interested in the channel. So this implies what happens to the signal in between the transmitter and the receiver. So that means we are interested in this part. And we would like to study the received signal at this point. And the received signal at this point is known as the noiseless received signal. And of course, this effect of AWGN noise or the components, analog components, they can be added on top of this noiseless received signal. But here we would like to study what happens to the signal that is transmitted from the transmitter and what is the effect of channel on the transmitted signal. So let's say we have transmitted a signal. This is the band pass signal from the transmitter, and this signal is represented by S of t, is equal to the real part of S tilde t, which is the complex baseband signal or the complex envelope of the transmitted signal, and this is the carrier. So now the noiseless received bandpass signal is given by RT. And how to write this RT? Let's say we have a signal. We have a signal S tilde t that is transmitted, that is a complex envelope of the transmitted signal that is transmitted from the transmitter. And this signal will undergo multiple reflections. So let's say this is one path. Let's say this is another path. And let's say there are some trees in between, and this is another path. So the signal reaching at the receiver from different path will add up at the receiver. So it is possible that the signal through this path will have some propagation delay of tau 1. Let's say signal from this path, it may have some propagation delay of tau 2. Or in general, we can say the signal that is arriving from the nth path will have a propagation delay of tau n. So this implies at the receiver, what we get is at a particular time t, we have a signal S tilde of signal that is transmitted tau n times before the present time. So we can write the signal as S tilde t minus tau n. This implies for the nth path, the signal has a propagation delay of tau n. So this is what we get, S tilde t minus tau n. Now each of these paths, due to the reflections, it may have there may be some change in the amplitude across the path due to this reflection coefficient, or due to this moving object or the surface of the car. There may be some reflections and it may have undergo some change in the magnitude of the signal. Or due to these trees, there may be some attenuation along the path. So as a result, each path will have a certain amplitude, and this is represented by Cn. So till now we have a signal that is transmitted from the complex envelope of the signal that is transmitted from the transmitter. It will undergo a propagation delay of tau n. And of course, the signal is either attenuated or it is improved. And thus we say in general, the signal is scaled by an amplitude Cn. Then the carrier term, in the carrier term, now it is not just a carrier frequency. We will have a Doppler shift that is encountered in the nth path. And the signal and also the time is t minus tau n, because we are experiencing a propagation delay of tau n at the nth path. So if we consider this term, this is the received signal from the nth path. But we are interested in the sum of the received signal from all the multipaths. So we will put a summation here, where the number of paths is equal to n to capital N. We assume there are n number of multipaths and we add up all the paths. So this is the received signal. So now in communication study, when in communication system, we usually study system by independent of the carrier frequency. So here we will separate out this carrier term. And then what we are left with, we separate out this carrier e raised to power j 2 pi fct. And then what we are left with is this expression. And this is the complete expression of the received signal at the receiver. When the signal is transmitted from the transmitter and it undergoes multiple reflections and reaches the receiver via multiple paths. And at the receiver, we add up all the signals and we would like to see the cumulative effect of all the signals. Now to simplify things, let us consider this phi n, which is equal to this part, and it represents the phase associated with nth path. And it can be seen that this is a function of fc into tau n. So at a carrier frequency of fc, we would like to see how much the phase of the signal has changed. We will look at, let's say, that in this propagation environment, let us now say that there is a slight change in the receiver location. Or we can say there is a slight, this moving object, it has moved a little bit. So now the propagation wave, there is a slight change in both the paths. Let's say the propagation delay across this path is tau 1, and let's say propagation delay across this path is tau 1 dash. And we would like to see the effect of small change in the path length of each of the path, and how much does it affect the phase of the signal. So let's say if we have the difference in path length is approximately equal to 1 nanosecond, and if we calculate this phi n, the phi n is approximately equal to 2 pi. That means the signal has undergo a full rotation. So what we can conclude from here, that even a small change in the path length of the signal can significantly impact the received signal strength, because it has undergo full phase rotation, and because of this full phase rotation there are signal strength fluctuations and it will impact significantly. And this is just along the one path we have seen. Now there are multiple paths, so there could be some path change across this path, or there may be some across this one. So in the end, we see if there is a phase change across this path, or there is a phase change across this path, or there is a phase change across this path. So if all the paths there are change in phase, so at the receiver we can see a significant impact on the received signal strength. So now if we substitute this phi n into this expression, we get r of t is equal to, is a function of the gains of signal, gain of the signal that is passes through the nth path, the phases along the path, and the transmitted signal that was transmitted tau n times previous to the current time t. And if we represent this part as r tilde t, we get the received signal as the real part of r tilde t e raised to power j 2 pi fct. And this expression is very similar to what we transmitted here as s of t. So what we want to study is what has happened to the complex envelope of the signal that was transmitted at the receiver and when it is received at the receiver. So in the next video, we would like to understand what happened to this received complex envelope of the received signal. The received signal.